There are many angles with the vertex in a wheel. These two spokes form a central angle with its vertex at the center of the circle. These spokes here form an inscribed angle with its vertex on the circle. There are also chord angles and tangent chord angles formed by the spokes on the wheel. There are also many angles with the vertex outside the wheel. A secant angle from 2 points on the wheel to the edge of the cliff, a tangent angle, and a secant tangent angle from the point of tangency and another point on the wheel to the edge of the cliff. The line from the bike seat vertically is also a secant because it intersects the circle twice. There are many relationships between angles and their arcs. The measure of inscribed and tangent chord angles is 1/2 the measure of their intercepted arcs. This can be proven by connecting the points A and C with the center and showing that the angle X is 1/2 the measure of angle Y. The measure of a chord angle is the average of the measures of the intercepted arcs. This can be proven by using exterior angles to show that the measure of angle X is equal to the measure of angle Y plus the measure of angle Z, and then by using the previous theorem about inscribed angles to show that Y is 1/2 of arc CD and Z is 1/2 of arc AB. Finally, the measure of an angle with its vertex outside the circle is 1/2 of the difference between the intercepted arcs. This can also be proven using exterior angles and the first theorem involving inscribed angles. A tangent is a line that intersects the wheel only once, so the ground is tangent to the wheel. A tangent segment is a line segment from a point outside the circle to the point of tangency or where the segment intersects with the circle. Circles can also be tangent. Tangent circles intersect each other at one point. They can be internally tangent or externally tangent. This old-fashioned bicycle, which is way too outdated for an experienced unicyclist like myself, has wheels that are tangent to each other. The two-tangent theorem says that the two tangent segments from a point are congruent. This theorem has many useful applications. For instance, it can be used for celestial measuring. Given an observatory on the Earth, the radius of the Earth, and the time it takes to disappear and reappear over the horizon, we can see how far away we are from something in space. Since the Earth rotates latitudinally, we are only going to be on the cross-section of the Earth with our latitude. Let's say we want to see how far we are away from an asteroid. AD is congruent to CD because they are both radii, and triangle ABD and triangle CBD share line segment BD. By the two-tangent theorem, AB is congruent to BC, meaning that these two triangles are congruent by SSS. So suppose the asteroid disappears over the horizon at noon and then reappears at 6 a.m. The Earth's rotation takes 24 hours, and it takes 16 hours between the two tangent lines, meaning angle X is 18/24, or 3/4 of the full 360 degrees, and angle Y is 1/4 of 360 degrees. Therefore, angle Y is 90 degrees. By CPCTC, angle G is congruent to angle H, and since they add up to 90 degrees, they are both 45 degrees. We know from trigonometry that tangent of 45 degrees is 1, and in this case, tangent of 45 degrees is also line segment AB over AD. And since the radius of the Earth is 3600, the tangent of 45 degrees is AB over 3600, which is also 1. Therefore, AB is 3600 miles. So we know from using the two-tangent theorem that we are 3600 miles from the asteroid.
Here we are going to prove that chords equidistant from the center of a circle are congruent. The lines extending from the center of the circle are perpendicular to the chords because they are closest at that point. First of all, we are going to draw two triangles. We know that their hypotenuses are congruent because they are both radii of the cake, and we are also given that the two distances from the center to the chords are congruent. Since we know that both triangles have right angles, we can prove them congruent by the HL postulate. Now let's look at the chords. Because the lines at the center are perpendicular to the chords, we know that they also bisect them. The halves of said chords are congruent by CPCTC, and the complete chords are congruent by addition. So now we know that any chords equidistant from the center of a circle, or from the center of a congruent circle, are congruent. can also prove that if chords are congruent, they are equidistant from the center. First, we drop a perpendicular bisector to each chord from the middle of the circle. Then we connect the center to each end of the chord to make two triangles. We know that the part of each triangle on the chord is congruent because the chords are congruent and bisected. We also know that the hypotenuses are congruent because they are radii. We can then prove the triangle is congruent by the HL postulate and then the distances by CP/CTC. Therefore, any congruent chords will be equidistant from the center of the circle. Now let's prove some angle arc theorems. Because we know that an arc is measured by the angle that defines it, if two arcs are defined by congruent angles, then they are congruent. Conversely, if two arcs are congruent, then their central angles are also congruent. Also, if two angles are congruent, then the chords defined by their intercepted arcs are congruent. We can prove this by taking the given congruent angles and the congruent radii and proving that the two triangles are congruent, and therefore the chords by CP/CTC. The converse is also true. If two chords are congruent, the central angles defined by the intercepted arcs are congruent. Finally, if two arcs are congruent, then the chords that intercept them are also congruent. Combining the previous theorems can prove this. Given the congruent arcs, the central angles are congruent, and therefore the chords are also congruent. The converse is also true. If two chords are congruent, then their intercepted arcs are congruent. These theorems have many practical applications. For example, let's say I wanted to build my very own Roman Colosseum and make it circular. Or if I want to be realistic, it could be a baseball stadium or even a circular house, but I feel like building something better. I want to model my Colosseum as closely as possible to the original, just in a circular shape. My new Colosseum will also be blue. The design is essentially a few concentric circles that will make up different seating tiers, and I want areas to be for viewing and other areas to be for vendors. The area that is below the horizontal line in this diagram would not offer a very good view anyway, so I decided to make it an area for people to buy food and souvenirs. Let's say I also want to have another smaller area for people to buy things on the other side of the stadium. I want the seating areas to be of equal size, both because I like symmetry and because I don't want people to have to walk too far to find food. I go out into the center of the arena and create two congruent angles that intercept the arc of the smallest circle. Because my stadium is already nice and symmetrical, the seating areas made by the new angles are now congruent. Now let's say I want to have overhead cameras that can look down on the stadium. I want them to be the same length, so I mark 2 points equidistant from the center of the stadium. I then run the cables that hold the cameras along so that they are now perpendicular to the lines formed by the lines from the center to the 2 points. Now my cameras can travel the same distance and can cover the whole stadium.